We're going to continue to explore the consequences that just go on and on and on about Cauchy's theorem. Um, the most general form of the theorem that we have right now is given by Theorem 5 in Alfors, which I will reproduce a little informally here because you have the actual statement available to you. So we've got a function f, and it's analytic in a region delta prime. Of course, it's complex valued. And but we've omitted a finite number of points. I'm just going to do it for one point because we talked about already how to extend that to any finite number of points. So what we have is that we've got an open disk delta, and we've taken out a point zeta. So you get a picture kind of like this one here. And so the function's not defined there. Ha 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 ha. You're going to find out the function actually is defined there, well, under the right circumstances. And then we have this limit condition that the limit as z goes to zeta, excuse me, z's not going anywhere, for z near zeta of z minus zeta times f of z. So I kind of called this a growth condition. I've said this is going to come up over and over. And you know what? It comes up over and over and over again. This limit has to be 0. So that's the same condition that we've been looking at in lots of other contexts. And we'll continue to look at in many other contexts. This is something that will come up over and over again. And that these together imply that if a gamma is closed in delta prime, a closed curve, then the integral over gamma f of z dz is 0. And so, and that's for every closed curve in delta prime, which is kind of strange because we've already looked at some winding number stuff. Okay, there's Cauchy's theorem. So, so we're just going to keep applying it. And again, let me emphasize, this is not the most general form of Cauchy's theorem yet, but we're going to keep applying it. We've got enough now to do some interesting stuff. So if we have f is analytic in a disk delta, and we have a closed curve in the disk. We've drawn that picture a bunch of times, and we've got this doesn't look right. Excuse me. We've got a point, and I think I wrote down in my notes incorrectly what I meant. So let me jump ahead a little bit. Anyway, we're going to yeah, I wrote down the wrong thing. Excuse me. Anyway, we have some point A that is not on the curve. And I'm really abusing the notation here. I'm confusing the name of the function with the image of the function. And so here's the image. These, in practice, are the same thing. But if you look at what's really going on with that notation, these are very, very different things. Gamma is a function. And how can a function be a subset of a disk? Well, what we mean is the image of the function. And so that's the curve. Okay, anyway, so this is a situation we've bumped into before. And we're going to define a new function, capital F, and that's a fraction. And the bottom is z minus a. And the top is f of z minus f of a. Well, by golly, you've probably seen expressions like this before when we talk about the mean value theorem. But the thing to notice here is that even though f is not defined at a, let's see what's going to happen. We know that the limit for z near a of z minus a times capital F of z, well, we've kind of rigged the game here because capital F of z has z minus a on the bottom. And so if we're not at a, those cancel. And this is just a little f of z minus f of a, and f is analytic and therefore continuous. So this limit is 0. So we're in the situation where we can apply Cauchy's theorem to big F. So boom, 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 integral over gamma of f of z. I'm going to write out the actual expression for big F of z. So it's still a fraction. Top is f of z minus f of a. Bottom is z minus a. Just substituting there. Well, that integral is 0. That's based on the Theorem 5 version of Cauchy's theorem. And so because we have that limit condition that's going to keep coming up. And so this integral is 0, which may or may not sound very interesting, but if we do a little bit of standard integration kind of manipulation, we can say, well, you know what that means is the integral of a fraction, f of z dz on top, z minus a on the bottom, is equal to the integral f of a is still a fraction. On top is f of a dz, bottom is z minus a. And this is a very, very interesting statement about integrals. And so the reason is that the second thing that we have here, this f of a is a constant. A is a fixed point. So f of a is a constant. That comes out of the integral. And what this really is, it turns out to be the winding number of gamma around A. You knew that was going to come up again. And I've skipped a 2 pi I in there, sorry. Well, I'll just throw in 2 pi I times f of A. Whoa. This gives us a way to calculate f of A, because if we know the winding number, and we certainly know what 2 pi I is, then we have f of A as being given by this integral. So this is the Cauchy representation formula. It's got other names. People have been real fancy about it, but it says integral over gamma of the fraction f of z dz over z minus a is, I'll get this right now, 2 pi I times the winding number. I'm just going to write n times f of a. This is an amazing formula. This is an absolutely amazing formula. And let me show you something that is not made as prominent as it might be. If you go back to the definition of capital F that did this, this is the same kind of thing that in the real domain, this would have been, oh, we're going to apply the mean value theorem here. And what we get here is that f of a is up to a constant. The average value of the function f averaged over all the points on the curve gamma. It's kind of like a mean value theorem here, but it's much, much, much more general and applicable. So there's a little bit of standard calculus that goes into this that gives us the following generalization. It says that the nth derivative of f at z, this is just by differentiating under the integral L4s, goes on for pages, but it's pretty standard stuff, is the following fraction, n factorial on top, 2 pi I on the bottom. And then the integral is, for some reason we're changing notation, but it's still a fraction. Top is f of zeta d zeta, and the bottom is zeta minus z. Sorry, I made an ugly zeta, but there it is. So this tells us not just the derivative, not just the function f, but the derivative of the function f and the second derivative and so forth and so on. And this leads to a kind of a crude estimate that we're going to need in a minute. This says that the absolute value of the nth derivative of f is in the disk D is bounded by m times n factorial times r to the minus n. M is the maximum value of f, absolute value of f on D, and r is the radius. So this is the Cauchy estimate. And from this, we get two very, very important and striking theorems by using this estimate, which is as follows. One of them is Morera's theorem. And the Morera theorem says that if you have a continuous function on some domain omega, not necessarily a disk, and you take integral around a closed curve, and you get 0 for every closed curve. So now kind of the variable in this function is the closed curve gamma. So I'll write this way. For any gamma, if the integral over gamma of f of z dz, so that's, some people would like to write that as a contour integral, but it's all integrals are other integrals. If that integral is 0 for every gamma that's contained in this region omega, that means that f is analytic in omega. And that's just a simple application of that Cauchy estimate that's right above it. So Morera's theorem gives you a way to test a function. Oh, come on, be real. You're not going to integrate it over every single arc, closed curve in the region, are you? But okay, it's still very useful. The other thing is that's a consequence of this. This is the Liouville theorem. We have to practice our Français. It's Liouville. The Liouville theorem, which says that if f is bounded and analytic, so that's pretty easy to see whether f is bounded and analytic, in the plane, then it's a constant. So there are no bounded analytic functions over the whole plane. That sometimes that's called an entire function. So some people might say there are no bounded entire functions. So f is constant. Ba-boom. And this is also a simple consequence of that Cauchy estimate. So one more thing, and this is the most striking thing of all to me. Well, there are a lot of things that are striking to me. This is one of the most striking things of all to me. So let's take a look. This is, by the way, Theorem 7 in Alfors. And what we have is a removable singularity. What is a removable singularity? It is, first of all, we can spell it right. Removable singularity, that's that limit condition. So we have the limit for z near a of z minus a, f of z is 0. So if that's true, then a is a removable singularity. Now the thing is, we're talking about singularity, so something is not defined at a, and what you find here is using Cauchy's theorem, and if you have a removable singularity, so if a is removable, you can extend a function f that's defined in a disk around a to a, and the way you do that is just by using this Cauchy representation formula. You can define f of a to be 1 over 2 pi I. I'm going to just assume the winding number is 1. Integral over gamma that has winding number 1 around a of f of zeta d zeta over zeta minus, zeta minus a. And so there are like no holes in these functions, because if you have a removable singularity, then you can find out what the missing value is by integrating around some, in this case, simple closed curve that has winding number 1. And so a lot of complex functions extend far beyond their originally stated domain, and that makes for a lot of very interesting things that can happen with these singularities.